Hello everyone. Today's lecture we will start with reviewing the probability theory that you might have studied already. Still we will refresh our knowledge on your elementary probability theory with little bit more emphasis on whatever we wanted to do. Okay. So let us confine ourselves in the beginning to discrete probability spaces, because that's what we are going to need in order to put the binomial asset pricing model into this framework. So, we will restrict ourselves to what we call discrete probability spaces. As you know, for any probabilistic or stochastic model, the underlying object is the probability space, which is what we are going to describe now. The first element of this probability space is what we call a sample space, which is nothing but the set of all possible outcomes of a random experiment, which basically describes the complete enumeration of all possible choices that might occur in the probabilistic model. Okay. So, we will denote the sample space by this capital letter omega, which is what we will going to call this as sample space. Now, on this sample space, okay, we are going to consider what we are calling it as an even space, which mathematically, if you have to describe, is given by a script letter f, which we call is a sigma field or sigma algebra. This is the sigma algebra is the language that those of you who might be familiar with measure theory would be aware, but in probability more often we may also use the word sigma field. Now, what is this? This is what is the sigma field here, right? Sigma, this is a non-empty, if I have to simply describe, it is a non-empty collection of objects, subsets of this capital omega, and that is closed under complementation and countable union. Okay. Which means that what? It should have three properties. One, phi, which is the null set, okay, belongs to F, which makes this as a non-empty. 2, if A belongs to F, then its complement should also belongs to F. 3, if you have sets A1, A2, A3 and so on, which are belongs to F, then union of this AIs should also belongs to F. Okay. These three properties will immediately imply two other immediate consequences for this property, which is basically my omega will belong to F, because phi belongs to F, and if phi belongs to F, then phi complement belongs to F. So, which is omega belongs to F. And the second, which is part A, part B is basically if you have A1, A2, A3 belongs to F, then its intersection of this AIs would also belongs to F, which you can see easily if you are aware about. Simply if you use A intersection B complement is equal to A complement union B complement, then this follows from these two, property 2 and 3. Why do we need these two? Because these two will help us to easily construct the sigma field in our cases. Okay. Now, typically in elementary probability theory, we will take this F to be the set of all possible subsets of a particular set, okay, which in this particular case mean that most often you might take this to be what we call the power set of omega. Whenever if omega is finite or if it is countable, this is most convenient to take this power set of omega as the sigma field, which will cover all possible events that we might think about with respect to this random experiment. But in our case, in financial mathematics, we need to distinguish between various sigma fields. So, we will be specific to certain sigma fields, and we will need to distinguish various sigma fields, and we view the sigma fields as if the information content. Okay. So, as we go along, you will understand what I mean. So, we need to distinguish various sigma fields, that is the first thing that we need. Okay. Now, in this particular case, suppose let us take a concrete example. So, let us take the experiment of tossing a coin 2 times. In this particular experiment of tossing a coin 2 times, my omega would then be consisting of these 4 possible outcomes, right. This is what we call as the enumeration of all possible outcomes of a random experiment, which is what the sample space. So, in this case the sample space would be this particular element. Okay. Now, in this case if I take the power set of this particular omega, which will have 2 to the power 4 elements, which is 16 elements is what then you will have in this case. But let us also take another sigma field. Okay. So, this is basically what we call the power set of omega. Now, there could be multiple sigma fields with respect to this particular omega. We just need to ensure that it satisfies the definition or it has the properties that we have specified when we define a particular sigma field. So, in this case what we have, suppose let us take another sigma field, say G, which is basically phi omega H H H T and T H T T. Now, if you look at this G, this is also a sigma field. You can verify easily that this satisfies all the properties of the definition that we have specified. Okay. So, this is also a sigma field, right. Like this, with respect to this omega, you can define so many sigma fields, okay, of which, right, the simplest one is what we call some f naught. Let us denote by f0, which is pi omega, which is what we call it as trivial sigma field. Okay. Now, as far as our information content is concerned, like this does not have any information, that is what we mean. If I look at G, then it is tells you about what events you know, what events you do not know, right. So, what events you know by observing Z, if you look at this particular sigma field G, this takes this HT as one event and this is its complement event. So, this set is a sigma field. Now, if I look at these two, this tells me that this is an event that the first toss is a head and this is an event the first toss is tail. So, essentially this G is the information content of the first toss, whereas if I take the F, the complete sigma field, which is the power set of omega, then it is the information content of both the tosses of this particular coin toss experiment, right. So, more about this we will come to know later, right. Now, let us move on. After having seen this sigma field and our view as sigma field as its information content, as our view as this is the information content. Now, we move on to the next part of this probability space definition, which is what we call this P, which is what we call it as a probability measure, which is the third ingredient of a probability space. Now, how do we define this probability measure? Or simply probability. If you are not comfortable with the word measure, it does not matter. So, you can just call this a probability function or simply as a probability. Now, what is a probability function? So, how do we define? So, we define a function p from where we write p is a function from f to r to mean r is the set of all real numbers here is a probability measure or simply probability if it satisfies the following properties. What are they? Property A is that it is non-negative for every event. Property B is it is normalized to 1, and property C or the third property is if you have sets or events A1 A through they belongs to F, and if they are pairwise disjoint, which means that AI intersection AJ is null set for I not equal to J. Pairwise disjoint, then probability of union of AI is equal to the sum of probability of AIs, right. Any function P, since it defined on the class of sets, so P is naturally a set function. A function P, which we call it as a probability measure, if it satisfies these three properties. So, there are a number of conclusions which one can draw immediately from this definition, and which are given, you might have be aware in the elementary probability ideas. So, that we will not go into that. Okay. Now, someone familiar with measure theory, you will know that this probability measure is nothing but a measure with of total mass 1, that is it. So, once we have these three elements, then we have the complete triplet, which is what we call it as a probability space. So, for any probabilistic model or stochastic models, there is always an underlying probability space. Sometimes you may be able to describe completely, sometimes this is hidden underneath, and you are happy to work with something which is defined on a particular probability space. Okay. Right. Now, once we have this probability space, right, next we define the notion of what we call a random variable. Right. Now, simply saying a random variable is a real valued function on omega. This would work as long as the sigma field that you are taking is the power set of omega, but since we need to distinguish various sigma fields and we might consider sometimes sigma field which is not the power set of omega when we define a random variable. So, if we have to define in general, which will also work across even the continuous time cases when omega becomes an uncountable sample space, then we need to define x as a measurable function. Okay, what do we mean by that? So, to be precise, so we say a function x from omega to r is a random variable if x is, simply saying, if x is f measurable, which is equivalent to say that this particular set, which is collection of all omega, such that my x of omega is less than or equal to a belongs to f for all a in R. For all real numbers a, if this is true, of course, you can define this in various ways, but we will take this particular way of writing. So, this is a function is if this is a random variable, a function which is defined on the sample space is a random variable if this particular object that we have defined is belongs to f for all a. Okay. The reason why we want this, because we know already that only say for sets belonging to f we have defined p. So, when later when we want to measure the size of this set, so we can immediately find the probability of this. Okay. Now, this particular set can be written in many ways. Sometimes for convenience, we will not elaborately write something like this omega such that x of omega less than or equal to a. We might conveniently write something like x inverse of minus infinity to a, right. This would mean the same as this set, right, or simply x less than or equal to a with either this braces or the other braces, whichever way you write it. So, this means that the set of all omega such that x less than or equal to a, or this means in this way. So, this x inverse of minus infinity to a is what would help when we write in general, even in general probability space. So, this is what is the measurability of this function means, and an f measurable real valued function defined on omega is what we call as a random variable. And note that when we actually define the random variable, the p does not come into picture, only omega and f plays a role. Okay. So, this notion of measurability is a very simple definition, but it is very subtle. Now, let us take a simple example in this particular case and see like how we can define and how we can relate to the sigma field that we have it here. Okay. Now, let us take the same example of tossing a coin twice, and in that particular case let x denote the number of heads in two tosses, number of heads in the two tosses. Now, if this is what my function is, right. Now, whether this is a random variable or not would depend on what f I pick. If I pick my f to be the power set of omega, then x is a random variable. So, let us write as RV for the random variable. If I pick g that we defined earlier as the sigma field, then x is not a random variable with respect to that f. that G, right. So, to be little bit more precise, let us see how and why this x g is or x is not a random variable with respect to this G. Okay. What we said that x should be measurable with respect to f. Suppose if I take this G as the underlying sigma field, right, then consider this particular set, say A sub A, to be this set of all omega such that my x of omega is less than or equal to A, right, and we wanted that for every A this set should belongs to f if x is a measurable, f x is measurable with respect to that particular G. Now, let us look at what are these events for various kinds of A. Okay. If I look at here, if this will be null set for all A which is less than 0, right. If I take any A which is, because this x counts the number of heads in the two tosses, so it can take possible values as 0, 1 and 2, because this is a 2 coin toss experiment. So, for any A less than 0 this will be the case, and for any A which is greater than or equal to 0 but strictly less than 1, this event would be this, and going forward for any A which is greater than or equal to 1 but strictly less than 2, you will get this set as this AA, and omega for A greater than or equal to 2. Okay. Now, if x is a random variable with respect to this particular G, then this sets must belong to G, but you obviously know, you can notice that this set either TT or TT, TH, HT, none of them belongs to AA. So, at least for at least one real number A, the test fails, and hence this x is not a random variable with respect to this particular G, but x is a random variable with respect to this f, because f contains all these sets. Right. So, this is what you need to understand, right, and by taking some A is equal to half, suppose if I take, then I will get this set as TT is the singleton element which is not there in G, and hence x is not a random variable with respect to G. So, x is not G measurable, but x is f measurable. Okay. Now, since we are working on discrete probability spaces, so what do we, when do we say S is a discrete random variable? So, a discrete random variable is one where or for which this particular omega such that my x of omega is some, oh my god. Okay. So, a discrete random variable is one for which this particular probability is 0 except for a countable number of, at most a countable number of A's, say A1, A2 and so on, such that this sum to 1, the probabilities are, this is the total mass of 1 is distributed on a countable set of points Ai such that the total mass is 1. So, the sum is over I. So, when you see here we are using, I mean, without much, so to say, without much difficulty, like you can say with little bit of abuse of this notation, flower braces as well as this braces, but this is fine. Okay, so you just have to. Now, in discrete case, especially, we said that okay, just now that x of omega less than or equal to ai is what you need to check the measurability of a particular random variable with respect to your sigma field. But in discrete case, to check measurability with respect to sigma field, it is enough if you consider this set is equal to f for all a in L. This is either flower braces or this braces you can use. So, if you check for a discrete random variable, it is enough that if you check for x equals a, if that particular set is in F, then x becomes F measurable. Okay. So, the reason is that you can easily observe that if you know x is equal to a, all these sets, then x less than or equal to a, since a only for at most a countable number of a's you are going to have. So, they can be written as union of countable number of such sets with equality. So, and hence this is sufficient to check for the discrete case this one x equal to a belongs to f for all a. Okay. Now, there is associated notion of the sigma field generated by the random variable x or the smallest sigma field with respect to which x is measurable. Okay, we said G is not the sigma field with respect to which x is measurable, but f with respect to f, x is measurable. So, what is the smallest sigma field with respect to which x is measurable? Okay. That, to define that, suppose if I have a class of sets, okay, and if I denote my sigma of this class C as the sigma field generated by this class C. I mean what? Suppose if this has some 2, 3, 4 whatever number of elements that we have, now by taking all possible combinations of unions and complementations, you form a sigma field which will contain that. So, that is what you call sigma field generated by the class C. This is notation. If C is a class of sets of this, then sigma of C, script C is a sigma field generated by C. Now, in the same way, we can also define the sigma of this x, okay, which is the sigma field generated by this random variable x. Remember, we are restricting currently to a discrete random variable. So, this is then would be given by, in one way, is the sigma field generated by sets of this class. Okay, suppose if I call this as a class, so the sigma field generated by sets of this form, okay, where my x inverse of ai, so I is equal to 1, 2 and so on, right. So, in this particular example that we have seen x as the number of heads in 2 coin tosses. So, you can easily see that this, the sigma field that I am writing, so this that I have written down here, the sigma field is the sigma field generated by the random variable x, and this is the smallest sigma field with respect to which this x is measurable. Now, if you see the f that we have considered earlier, which is the power set of omega, contains this sigma x, right. So, you can see that this sigma x is contained in this f, which is the power set of omega, but this sigma x is not contained in G that we have seen, because this, and in this you would see that actually if I look at these three sets, the red underlined ones. So, these three, if you look at it, has something we need to say about it little bit. So, this 3, if I look at x inverse of 0, if I look at it, I will get Tt, x inverse of 1, because the x takes value 0, 1, 2. See, x inverse of 1, if I take, I get Th and Ht, x inverse of 2, if I take, I get Hh. Okay. So, these 3, in fact, if I take the union of these 3, I get my omega. So, these 3 sets are what we call a partition of this omega. They are disjoint and their union is omega. Such sets are called partition of omega, and these 3 is what we call atoms for this sigma field, right. So, these are the 3 coerced partition that you could have with respect to this omega, which generates this particular sigma field sigma x. So, this is what we call atoms for the sigma field. Of course, if you are not familiar with the terminology, it is fine, we do not need that, but what information this tells. This also tells an information. Again, we come back to that point, why we wrote this sigma x is that sigma fields is our information content for us, and this particular sigma field, what is the information that it tells is that if I look at these basic sets, so this is either, I mean the partition sets are the atoms. If I look at it, I will get, I know exactly what is the information that this particular, a particular sigma field, or that matter any sigma field will tell. In this particular case, if I look at Tt, this is x is equal to 0 case, and this is x equal to 1, this is h. So, what is the information that it tells is that it has happened either 0 het or 1 het or 2 het. This is the information content, and all associated things. Suppose if I look at this Tt, Ht, Th, that is basically tells at least one tail or at most one head, I mean whichever way you want to describe the events. Okay. So, it is all depends on the number of heads and number of tails is what then you get this information content. Okay. This is if I look at with respect to G, which tells about the information about the first task, whether the first task is a head or first task is a tail. In this case, it is now talks about the number of tasks. So, this is the crucial point when we model in the quantities, various underlying states of the economy in financial markets, that a sigma field we always view it as information content, and this is what it is. Okay. So, given a discrete random variable, okay, we also know another quantity that we define, which is basically the expectation of x, which is defined by expectation of x, which is basically sum over x over all x, such probability of x is equal to x, provided the sum So, we define expectation of a discrete random variable by this definition, provided the sum converges. Whenever x takes a finite number of values, of course, this convergence of this is guaranteed. So, we will not worry too much about that, but whenever this x takes a countable number of values, of course, you need to worry about the convergence. And then in the elementary probability theory, like you say that this is provided this sum converges, you say that expectation of x exists and is defined by or given by this particular quantity. Okay. There is an alternate definition which is equivalent in the discrete setting, okay, which we will just expand this and then we will see we are able to reach that particular definition. So, let us see this is equal to so, this probability x is equal to x, I can write it in this form because this is for some omegas gives rise to the same value of x. So, which I am separating and I am writing it in this form. Now, this particular x, because for all those omegas which gives the same value of x, so I can push this x inside, I can write it as x of omega because I am constraining my x of omega to be x only for all these sets, right. So, you can write it in this form. Now, what we have here, this is equal, sorry, this is equal. So, what we have now is that you picked a particular value of x and you have written the sum inside and you have summed over all possible x. So, if you relax, what you would get is essentially this. Okay. So, so expectation of x, which in the elementary probability theory you write it in the as in the first line defined by, it is also equivalent to something which we have written on the last line, where we are writing it as in terms of omega, small omega belongs to capital omega of x of omega, probability of each of these omega. So, this is same, and the advantage of this is would be clear as you go along, and certain properties of x, say for example, if you want to show expectation of x plus y equal to expectation of x plus expectation of y, if I use the original definition, it will be some distance before I prove that, but whereas if I use the last part, it is immediately clear. So, like that we will have certain advantage, and also notationally when we use it later, you will see that the second definition is convenient for us to use. Now, once we define expectation, now we also recall the notion of independence of two events. Okay. We know that two events are independent if this satisfies this. Remember, when we say independent, we mean probabilistically independent or stochastically independent is what we call, not our intuition or what we might think that something should be independent of this, right. We talk in terms of probabilities. So, independence of two events in terms of probability is basically this, which is what you know. Now, similarly, we also say two random variables are independent. So, what do we mean by that? We also know that probability x belongs to A and y belongs to B if you can write, of course, this is not precise correct to write subsets of, I will not write this way. Not all subsets, but in this case discrete it is fine that you can write. So, when assume that two random variables, assume that they are discrete random variables. So, x and y are independent if this is true. Similarly, now we can extend this idea, or we can write generally this, that two sigma fields being independent of each other. Okay. So, we can say f and g are independent if A and B are independent whenever A is in F and B is in G. So, for every A in F and for every B in G, if A and B are independent, then we can say that these two sigma fields are independent. Okay. Similarly, you can talk about a random variable x and a sigma field G being independent. We mean exactly similar. What we mean is that, suppose if we have to say x, a random variable x and a sigma field G are independent if probability of x belongs to A, where A and B are as usual subsets of real numbers, is intersection B is equal to this whenever A is a subset of reals and B is in G. So, this is same as saying that a random variable x and a sigma field G is they are independent, is the same as saying that sigma x, which is the sigma field generated by the random variable x, or the smallest sigma field with respect to which x is measurable, this and G are independent. Because if you look at sigma of x, the sets inside the sigma of x is nothing but x belongs to A. So, it is essentially that is what then we are saying. Similarly, when you say two random variables are independent, what really mean is the underlying sigma fields generated by each of the random variables, they are independent. Okay. So, this is just the notion, the same notion that you are aware, but we are just slightly putting it in a little general framework. Now, to see an example of sigma fields being independent, suppose you consider the same two coin toss experiment, and let us consider now two sigma fields, which is this. If I look at these two sigma fields G1 and G2, okay, I mean if I go back to the notion of information, and you can observe that the G1 is the sigma field which tells about the result of the first task, and G2 is the sigma field which tells about the result of the second task, right. Now, these two G1 and G2 are independent if, say for example, if I assign each of them value 1 by 4. Suppose if I assign, because as I said, sigma fields we can write down, but the sigma fields being independent or dependent will be decided by the probability measure, because we talk independence in terms of probability. If I assign this one, you would see that these two sigma fields are independent, but if since I can assign in arbitrary manner for these 4 elementary events any value, any non-negative value such that they sum to 1, if I assign in some other way, you might see that this may not be independent. Okay. So, that is why you need to keep in mind that dependence, independence, first coin toss independent of the second coin toss, right. So, that would essentially mean this, or you can even write in terms of in general, somehow generically you can write, but does not matter, this is the simplest example that you can think about. Suppose if I assign arbitrarily, say for example for HH, HT, TH, if I assign 1/10 each and TT the remaining 7/10 of the total probability 1, then you would immediately see that these two sigma fields are not independent, because you can take any one appropriate set from each of these and then see that it does not satisfy the required equality property. Okay. So, that is what you need to remember, and whenever they are independent, you have certain advantages, right. So, you can say that, for example, one immediate consequence that you would find is that this quantity would be equal to this if they are independent, okay. Right. So, expectation we have defined. Now, similarly you can also define other moments like variance and higher order moments, as and when we need we might. Okay. Now, when we come to the final part of it, okay, we close this review with the notion of conditional probability. Okay. So, the probability of A given B denoted by probability of A given B is defined by, you can say, probability of A given B is probability of A intersection B provided probability of B is greater than 0. So, this is sometimes you can also write as, if I write PB of A to mean the conditional probability of A given B, which is exactly equal to this, which is equal to probability of A intersection B by probability of B provided probability of B greater than 0. So, this is what is defined as. Okay. Now, once we have this, I mean one can easily observe that this also defines a probability measure. This PB itself is a probability measure on the probability space B, F intersection with B and PB will define a probability space. Okay. So, that anyway is not important at this point. So, you can also observe that it also defines a inducive probability measure. But what is relevant for us is the following. This probability measure would also induce or when we define a random variable on this, we can also define the conditional expectation of a random variable x given b is defined to be this x given b, which is equal to, which we define to be expectation of x I b by probability of b, where what is this I b? It is an indicator function of omega, which is equal to 1 or 0 if omega belongs to b and omega does not belongs to b. So, it just gives value indicator function of this. Okay. So, this quantity, if we go further, is what we define to be. Obviously, when we define this, we also know that this is defined to be for probability of b greater than 0. If not, we cannot define this. So, the conditional expectation of x given b, just like probability of a given b, we define in this manner. The conditional expectation of x given b is given to be this, which you can easily see that what we wrote here is expectation of x indicator function of b, probability of b. Now, expectation of x indicator function of b, you can write, if I write you can write in this manner, because x indicator function of b, if I write if I apply the usual expectation formula, and if I notice that I b gives value 1 for omega belong to b and 0 otherwise. So, this is nothing but the sum omega belongs to b of x of omega p of omega divided by p of b, which you can see that connected to this So, this conditional expectation of x given b is nothing but the expectation the normal way when you define, but with respect to the induced probability measure P b, which is the conditional probability measure that you have it here, right. So, let us summarize in this lecture what we have done. We have just refreshed our idea of finite probability spaces, discrete probability spaces, especially finite probability spaces. We defined what is a probability space omega f p, the triplet, and in the process in the sigma field, our view was that we view it as if it is a information content, and we also define the notion of a random variable not just as simply as a real valued function, but is a measurable function with respect to some sigma field. So, if you take any general sigma field G or F, then a measurable function with respect to that is what one call it as a random variable. And then once we have that, then the independence notion again in terms of sigma fields and conditional probability, and additionally finally we ended up with conditional expectation of x given an event b. So, here we just finished with an event b in this lecture. So, we will expand these ideas in the following lecture. Bye.